what's going on. Our device consists of a 32-bit ARM controller. This sounds a bit overpowered, but concerning the fact that we are not planning to sell it in high quantities, that this is meant to be a device for open source projects where you have as few as possible initial costs. To my knowledge, there is no reasonable 8-bit compiler for microcontrollers in open source world. So you want to stick basically to 32-bit compilers. The cost difference between a 32-bit CPU and an 8-bit CPU is only a few euros. So for a small volume project, it definitely doesn't matter. The idea is that, or our intention was that with 32-bit architectures, you get far more people that can contribute because there are no special features of 8-bit world to be considered. You basically program the same language that you use on your computer. And this is what we wanted to achieve. The library and the firmware we provide to you provide really high-level functions that you already know from host computer world. We have functions like printf, where you can print messages on debug output, so you can quickly find errors and you can develop your stuff without having to know about the very internals of the CPU. Basically, it's shielded by our API. Maybe we'll ask that why we used this proprietary RFID reader IC, this RC632. The idea was that we wanted definitely to support MIFARE cards. The MIFARE cards are the cards I mentioned before that are used for transportation purposes and for example, as access control cards. The disadvantage on this card is that the cryptography algorithm behind it is not documented at all. So currently there is no possibility to talk to such cards unless you use the RFID reader ICs provided by the very same manufacturer that manufactures the tags itself, in this case NXP. So basically we only use this for providing MIFARE support, and I think this is inevitable if you want to have a RFID reader. The RFID reader IC natively supports ISO 14443A and B and 15693. But we wanted to provide also support for proprietary cards that are not directly supported by the reader IC itself. To make this possible, we provided an interface where you can basically bit bang arbitrary bit pattern on DMA accelerated output. So this. Okay. Huh? I don't know what they did. They cut off all the high frequencies, and you only have the low frequencies, and you have all the. I try this. Hopefully, this is better. Okay. The idea we had is that most of the protocols that are involved in this technology need well-defined bit patterns that fit to the oscillator frequency of the RFID reader field. So to make this possible in this device without breaking your fingers when programming, we basically took the carrier frequency of a 13.56 megahertz reader IC and feed it back into the ARM controller and use internal timers to scale it down to a frequency we want to have, basically the baud rate or whatever. And then we put this frequency again on an output pin, which is fed back into the reader IC again, and works as a clock for the DMA interface. So this means that you can time your whatever protocols you decide to use, you can time them very exactly to the reader reader frequency, 13.56 megahertz. So you don't have to do the timing in your software. You just can pre-compute the bit patterns, and you just start a DMA request, and they are constantly clocked out at the baud rate you expect. And this solves a lot of problems for you when emulating stuff. And with this approach, with this time ICs, you also have the possibility to change, for example, the pulse width, and you can, for example, change the phase of the clock signal as you want. So you can do really nice tricks with this approach. For people that want to have complete access over the device, we provide a JTAG debug interface. We didn't solder the header by default because you have to spend up to several hundred euros to get such a device to be able to debug such code at assembler level. But I think most people won't need it. The debug interface is good enough. You can do printfs, and the most hairy stuff is solved. Harald wrote a great bootloader, which is able to be refreshed instantly during runtime. It only takes a few seconds, and you get a new firmware. You don't have to press strange key combinations or buttons on the device. You can instantly flash them, and this results in a very quick programming style, because you can, for example, create a target that says make install, and it immediately uploads the changed code, and with the debug interface you have perfect overview what's going wrong. So what we want to achieve with this talk is to take the fear away from you that, oh, embedded design, it's so crazy, and all the strange routines that nobody understands, and it's so abstract and whatever. But we tried to make it look as common as possible. You find all the routines you need there, and you have very high-level functions, and you can execute them without having to know what happens below. So I think for most people, JTAG isn't needed. What we also wanted to achieve, we intentionally choose a relatively big microcontroller. We don't use it that much flash for the common read applications, but the basic idea is that you can store the complete RFID protocol code inside the reader. This means that you can attach, for example, the reader on a door, and you can use one of the I/O pins we provide or the serial interfaces to, for example, trigger door contacts and stuff like this. You don't need a PC to solve this. So we try to provide you reasonable interfaces. For example, with I2C, you can directly attach displays. For example, you can display the name of the person coming in or whatever. Or with you can reconfigure the I2C pins to I/O pins. This enables you, for example, to trigger relays and whatever. So all the code can run inside. It fully understands RFID cards. It can do anti-collision. It supports multiple cards in the field. You can even detect what cards are in the field. It's very convenient. And you can test your code locally in your host computer, and you can recompile, cross-compile your code and have it installed after testing on your inside your firmware. So this is how we want to achieve that you have as few as trouble possible. And another idea is that oh no, okay, let's skip this. This is how the reader looks like. We wanted to keep it as inexpensive as possible. You have this standoff spacers, so it's basically on the PCB. You just turn it upwards, and surrounding the reader there you find the embedded antenna. The trace you see running around the top and bottom layer on the picture is not the antenna itself. It's just a shield to protect, to remove the electrical component of the field, and only use the magnetic component. The real antenna traces run inside the second and third layer. and you can see how the internal structure looks like on this slide. On the red one is the top layer, and the second one is the intermediate layer, where you have 2 turns of the 4 turns. You can see them on the dark red part. You also have the possibility to adapt it to external antennas. We used 0-ohm resistors to connect this antenna. You just remove them, and you have a 3-pin 2.54 millimeter spaced header to connect another antenna and do whatever you want. So basically you have to do your own antenna adaptation in this case. And if you want to do boosting of the signal to achieve bigger reading ranges, then you can tap into this interface too. So just to be aware what the current reader can do is, so usually the reading distance for this kind of reader without boosting is depending on, naturally depends on the card, because some cards use protocols which make it much easier to be read from a remote, from a far distance, and other cards simply take up too much power. So the reading distance is between, say, 8 centimeters down to 2 centimeters. The nice thing on this device is if you want to really learn something about protocols in there. For example, you want to see what actually happens on the RF interface when you're issuing comments. You have 2 possibilities. There are 2 interfaces called MF-in and MF-out, and these enable you to see intermediate coding and decoding stages of the this RFID front-end chip. So, for example, you send data, and you can see that the unmodulated data, and you can see the encoding, and can trigger to it, and you get a pretty good idea what happens on the interface. And for example, if you try to increase the range, you can see what changes what happens in the digital part if you, for example, increase the range and whatever. Also nice task if you're interested to find out about not well documented protocols is that at the same time you use, for example, this undocumented functionality, for example, by talking to MIFARE ICs. These are completely handled transparently by the reader IC. Basically, there is only few knowledge about this. You can issue this comment. The comment is translated into RC632 action, but you can, in parallel, you can sniff what happens, what the reader sends to the tag actually. So this is, for example, a nice use case for this MF-in, MF-out interface. And also this is the place you want to tap in if you want to support protocols that are not supported by the chip natively. There you have the same approach. You get the oscillator frequency, 13.56 megahertz. You use the timer input to derive the clock frequency you intend. You can adjust this, the phase, and you configure your DMA output to sample or transmit the data that you can pre-calculate. So this makes emulation of protocols that are not supported very easy. This is an example I just want to show what you can see. You see the data, then the first encoding step, and the resulting pattern on the RF interface. And this is on the RX side, you see the load modulation pattern and the resulting decoding steps. To have this easily accessible, you have to be aware that the reader provides a strong magnetical field. So if you just tap your oscilloscope probe there, you get a lot of noise by the carrier frequency, and so you get a huge amount of distortion. So we decided to use this U.FL connectors, which you know already well from wireless LAN cards. These are these very tiny HF connectors.